And then we'll start. Hey. Okay, it's a bit better. My heart's back in place. I'm glad that not everyone's gone.
Oh, you mean passed out and died from the test?
Yeah.
Oh, okay. Yeah, no, there are 2 students left.
That's good. That's good. I think once we release the results, everyone will calm down and we'll realize that the mistake was on our part.
Wait, mistake?
I mean, the results are lower than what we thought, and it's because we haven't covered something that I will cover today. So we think, well, we talked about it yesterday, and we think we haven't done enough algorithm design with you guys. So today I have problems, and we're going to come up with solutions.
You're not going to tell us about Kaplan numbers?
It's in the lecture notes. It's actually quite boring. I promise it's really boring.
Okay.
And if you want, we'll do that next time when we'll actually talk about numerics. The thing is, numerics are straightforward. Once you learn the algorithms, you're not going to come up with a new one. I'm pretty sure about that. Like, you're not going to come up with a revolutionary way of adding 2 numbers. So,
I don't know. Never know.
well, you can tell me why. Think about it, and you can tell me why you're not going to. Okay, so let's start with a problem. We know what sorted arrays look like, right? 1, 3, 5, 6, 7, 9, 12. This is a sorted array. If we're given a sorted array, we know how to find a number in it, right? What's the running time for that?
You mean any given number?
Yeah.
Binary search.
Well, what's the best way that we know?
Log n.
Okay, log n binary search, right? Well, instead of this, we're given a shifted array. And shifted means that, say you're shifting the array by k elements. We're taking these guys. So the array is shifted to the left. So these k elements end up on the right. These n minus k elements end up on the left. So 7, 9, 12, 1, 3, 5, 6. So still n elements, the array is shifted by some number k, and I want to find one number e in the array. I don't know k, by the way. We just know that it's a shifted array. This is 12. So the first thing you do is figure out how much time you have for this, right? If you're on a test, you roughly know how much time you have for each problem. If you're on an interview, you have to figure out how much time the interviewer is willing to give you for a problem. And spend the first, I don't know, a third of the time thinking maybe. Come up with the best solution that you can, and then stop there and start talking. So the first thing you do, you want to make sure that when you run out of time, you have something to say. The most awful thing you can say is, dude, I'm going home now. Or leave the answer blank. If you leave the answer blank, we're not going to give you points, right? So not good. So what's the worst answer you could give us? So, sorry? No, okay. So, okay, worse is a bad term. What's the brute force solution to this? A solution where we don't care about the running time, but we want a correct answer.
Look everywhere.
Yep.
So
do a linear search. Pretend we don't know anything about this array. Lose the information that it's a shifted array. Linear search, running time, order n. Okay. So this is something. At least now, when your time runs out, you have something. You're not going to leave empty-handed. Let's start thinking now. Next step.
Sorry, why we shifted again?
So the fact that it's shifted means, so originally it was sorted, right? But now, instead of it being completely sorted, you have all the elements are shifted to the left.
Yeah.
And then, so there's a rotation thing going on here.
Yeah.
So these elements got out of the array, and then they were put back in from the other side.
Why do we do that?
That's how the input looks like.
Oh.
We don't do it. It was done to us.
Okay. So now what do we want?
We want to find an element,
Oh, I see.
despite the fact that the array looks like this.
Do we know that the list that we have is shifted already, or?
Yes. So we're promised that this is a shifted array. So it will look like this. but we don't know what k is. If we knew what k is, could we do something fast? What would we do?
Yeah, you just reshift it back.
Yeah.
Right? You just hop off.
Okay, so if you reshifted, what's the running time?
Order n.
Order K.
Okay.
Okay, so if we actually reshifted and then do a binary search, it's order k plus log n. So for big k's, that's not better.
Why is it not order n plus log n?
I mean, you can say, since we don't have any promise on k, it's n. It's order k if you can shift things out of both ends. With Pythonless, it would be order n. Just popping out one element is order n in a Python. So this is assuming a smart array. Otherwise, if it's Python, good point. It's straight up order n. OK, so now another good point. You have this solution, and you have the brute force solution. They have the same running time. You run out of time. Which one are you going to code up? Which one are you going to show?
Simpler one.
The simpler one, excellent. So the reason is, if you're on a test, it's probably give the pseudocode, then analyze it. If you're on an interview, the guy will ask you, OK, what's the running time? Code it up on the board in C, Java, whatever he knows. So you want to code the simple solution because that reduces the chance that you'll have bugs. So that gives you the most points. So this solution shows more insight, but it doesn't have a better runtime. You stick to the simple solution. However, if you have this, then you have some insight on the problem, so you can keep going and hope you can come up with a better answer. So if we knew k, one thing we could do is reduce the array to an unshifted array. What's another thing we can do? So I claim that if you know k, you can come up with a reasonably easy log n method.
Well, if you're doing binary search, like you could just pretend like the arrays all together, but if you know k, so like let's say you're looking for 6, then you'd say, oh well, I'm going to split the array in half, but you're actually going to start at k and then split it in half. So it's like you pretend that.
So what you
Yeah.
want to say is you have a pretend array in your mind, right?
Yes. It's all shifted by k.
And you want to access the middle element to see if what you're looking for is bigger or smaller. Instead of looking at the middle element here, you look at the middle plus k, right?
Yeah. Oh yeah, there you go, plus k.
This is one way of doing it. Good running time. The problem is it's hard. You'll have to rewrite binary search and hope it works. What I would do, given that I had a bit of time to think about it, is this is sorted. This is sorted, right? So 2 binary searches are also going to be log n time. 2 binary searches, 2 lines of pseudocode. The running time analysis is pretty simple. Correctness is also pretty simple. And also, this gives me some insight on the rest of the problem, I claim. OK, so if we have k, we can do log n. What if we don't have k? What do we do? Yes?
You can figure out what k is.
All right, let's try to find k. We know how to do it if we have k. So let's try to find k. If I want to arrive to a solution that's log n, how much time can I spend on finding k? OK, so let's find k in log n time.
Binary search for minimum.
Binary search. So I like binary search because binary search is an algorithm that runs on an array. And that runs in log n time. So if I'm able to make it work, I know everything's going to be right in terms of time. So what do you want a binary search for?
Smallest number possible. I guess that's kind of going through all of them, though. That doesn't really help.
I think like.
So if you had the min, sorry, you can speak in 1 second. So no, if you can have the min, I think it's good insight. So if you knew where the min is, you know this is k, right?
Yeah.
So this is the minimum. That's good. OK, what are you going to say?
Oh, like for just binary search, simple, like not thinking about minimum or kind of thinking about minimum. Like I was thinking that if we start at 1, like we'll see to our right and left, and the point where like k shifts are ending is where we have like something larger to our right and something smaller to our.
Okay, so there's a discontinuity here. That's what you're saying, right? So this is sorted, but then at this point, this breaks.
Yes. So we are like kind of finding that point where something to the right is greater than me and something to the left is also greater than me.
Okay, so let's see if we can do that. So for binary search, you have to go somewhere. So in our case, we're trying to get k, right? And we know that it's somewhere between 1 and n. And what binary search does is it makes a guess. It says, hey, I think it's in the middle of the array. So it will probably guess n over 2. And it makes a guess, and you have to tell it, was the guess too small or was the guess too large? Because this is what allows it to recurse on either the left interval or on the right interval. The problem with the discontinuity is if I guess here and if I guess here, I still don't see the discontinuity. So it's good inside, but it's not enough. I need a little bit more. Yes, 2, 3, oh wow. You guys all got it? Let me see.
So I think we can like arbitrarily take the halfway point, so subtract it from the first element, and then like if it's a negative number, then like the discontinuity will be this half. If it's another, it'll be the other half. And then
Okay.
you can recurse on that.
Okay. Yeah. So let's draw this up. So in a sorted array, the numbers look like this, right? In a shifted array, we splice it here, and this guy goes to the right. So it's like this, and then like this. So this picture shows me the insight that I had before, that this part is sorted and this part is sorted. The missing part, which I just heard now, is that since the whole array was originally sorted, this guy is smaller than this guy. So if I draw a horizontal line here, I can draw a horizontal line somewhere, and this will not cross it. So this whole thing is taller than this. So, by the way, k was where the discontinuity was, right? You said discontinuity. This is k. It's somewhere here. So this is a better. So if I make my guess and I land somewhere here, I can know that my guess is too big because it's below the line. If I make my guess and it's somewhere here, I know my guess is too small because the number that I see here is above the line. Who says the line? The first element here. So this is how you look at it graphically. If you don't want to look at it graphically, this was a sorted array. If this is the kth element, then everything here is smaller than it. So all these guys are smaller than the first element. Okay, so honestly, who understands the solution? 3, 4, okay. Oh, okay, pretty good. Do we want to code this up, or do we want to look at another problem? Okay, who wants to look at another problem? Clear majority, all right. Usually I have to do both choices because not enough people are paying attention to get this. So I am happy. Yes. All right, so before I start another problem, one thing I want to say. Not only do I have a solution for this problem, but I have a process that allowed me to go from nothing to a few partial solutions. And while I was doing that, I was getting insight, and I was making sure that if I run out of time before I have the final solution, I don't walk out of the room empty-handed. So I don't just want to show you the final solution, I want to show you the process. You can look at the notes and see the final solution. That's not everything I wanted to get out of this. Okay, problem 2 has a heap. And this is a minimum heap, so it looks like this. So this is a minimum heap, n elements, and I want to extract the kth smallest element in the heap. So if k equals 3, this is the third smallest element, right? K equals 4, it's this guy, 5, and 6. 1 and 2 are here. OK. The good running time that we want, because this is a hard problem, so we give you the running time, is k log k. However, before we do that, I want to hear some brute force solutions.
For all of them.
And?
Oh, and
OK, you need to sort them first.
yeah.
So this heap is actually an array, right? 2, 5, 7, 6, 8, 6, 9, 8, sorry. So you're saying sort the array, then kth element. OK, what's the running time for this?
And log in.
All right, we have a solution. We're not going to leave empty-handed. OK, let's try to go a bit better. What's another way of doing it that will give me a better running time?
You could pop 5 k elements off of the...
All right, so this is a mean heap, right? So it has find min. And find min runs in order log n. So if I call it k times, I'm going to get the k smallest elements. By the way, heap sort says pop n times, and you'll have all the elements in sorted order. So we're doing a heap sort, except we stop when we lose interest after k elements. So we're down from n log n to k log n. So I would be interested in hearing a solution that's worse, because it would look like n log k, but shows me more insight. So by the way, this is good. You're already k log n. So k log n, the correct answer is k log k. Small difference, right? It's a logarithm factor. So at least it's not an n factor. If you code this up, chances are we're not going to be able to distinguish between this. So you'll never see this on a p-set. So you're almost there. And this is just applying straight up knowledge that we had before. Let's look at this solution, if anyone sees it, before we attempt k log k.
Wait, but in the other case, if we just pop off first k elements, why would that be the log n? Because it's actually an array, so I would think it would just take k time.
So this is a heap. If you don't maintain the heap invariant after you do the first pop, you're not going to be able to do the second one.
I knew that.
OK, cool. So let me give you a hint. How would we find, if this is an array, how do I find the minimum? 2, 5, 7. Did I forget something? No. Let's pretend this array doesn't start with 2, because it's boring if it starts with 2. How do I find the minimum? I keep one variable that says the best I've seen so far, right? Best seen. And oh, this is still boring. Let's start here. So we start with best seen equals 7. Then when we go to 6, we see, is 6 better than best seen? If so, replace best seen with 6. If not, keep going. Then I get to 9. Is 9 better than best seen? Nope. Keep going. Is 8 better than best seen? Nope. Keep going. So I compare every element with the best seen. And then whenever the element is better, I do a replacement. And then at the end, best seen will have the smallest element. So this algorithm works for k equals 1, which isn't very useful. So can we generalize this somehow to... So we have a running time here that might give you a hint about how we want to generalize it. And I want to generalize it for all values of k.
You can go to the power of 2 that is less than, the nearest power of 2 less than k.
OK.
That element, and iterate forward with your best scene. Does that make sense? If you want the kth, so if you want the 10th smallest element, right, then it has to be after the 8th row, the 8th. Because it's the next level in the tree. Does that make sense? That doesn't make sense, right?
It makes sense, but I don't think it's right. So you're thinking the 10th smallest element has to be somewhere below, right?
Yeah.
Uh,
Below the 8.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then pretend there are numbers here. 11, 12, 13, 14, 15. Do you see what I'm saying? So this is a heap. So I can keep filling it with bigger elements, and 10 is here. However, you can do something else to limit the size of the heap. It would give us a different running time, but you can do something. You can think about it. How can you chop up some of the heap? For example, if I have a heap that's 10 deep and I look at the 4th element, what can I do? You can think about that. And let's try to get to this. So I'll accept an answer for either how do we limit the heap in that case, or how do we generalize this algorithm? Yes?
Since you want to sort of remember the smallest k elements,
all right.
You make a max heap out of the k size k.
Okay, so I want to have, I'll break down your solution into parts. So you want to have a bag of the smallest k elements, right? So instead of the best seen, you want to have the k best seen. And once you have a bag, you want to go through your elements, and then if you have something that's better than what you have in the bag, you want to put that in the bag. Suppose k equals 3, and I have 2, 5, and 7 in the bag. And I see 6. Who do I want to compare it with? The biggest thing in the bag, right? So if I want the k smallest elements, if this guy is smaller than anything, these aren't the k smallest elements anymore. So I want to take the maximum in the bag, compare it with what I'm seeing right now, and if what I'm seeing is smaller, I want to replace it.
So that would be a max heap then. You actually want to
Yep.
flip. Okay.
So because I keep doing this maximum, I keep asking this maximum question, this has to be a max heap. That's why he said max heap. So you did all these steps at once, and then gave me the final answer. But this is how you do it step by step. So it looks like finding the minimum element, except you have a bag, and that bag has to be a maximum heap. And the original heap is a minimum heap. So the fact that you have to use a maximum heap is a bit non-trivial. Good answer. All right. So we have k log n, and we have n log k. So choose what you want to have in your log. We have a solution for you. How about this? How are we doing here? So suppose I'm looking for the 4th element, and my heap has 10 levels. How can I chop it? How can I reduce the number of things I'm looking at?
You can reduce it down to 4 levels.
I can reduce it down to 4 levels. Exactly. So if this heap has log n levels, and my k is smaller than log n, I can reduce the heap down to k levels and discard everything below. And the reason for that is we have a min heap, right? So if we go down on any path from the root to a leaf, the values have to increase. Right? Otherwise, it's not a min heap. Otherwise, there's an invariant violation somewhere there. So as I go down on any path, my numbers are going up. So these are all the paths of length 4. All of them have to go through here. All the paths of length 4 will stop here. So I know that everything here has to be bigger than the first 4 elements. So if I reduce this to k, and I discard everything else, what's the running time? So if I use my extract min algorithm before, what's the running time?
It was
I wish.
You're going log k, right? Like,
So it's-
find something.
So it's not.
Oh, sorry, it's k. Never mind.
So what's one operation in a heap? If I have the height of a heap, what's an operation? How much time does it take to do one operation as a function of the height of the heap?
Okay.
So if my heap has h levels, in this case, h happened to be log n. It's order h. So if I reduce it, I'm not reducing it from n to k. I wish I could. I'm reducing it from log n to k. So for really tiny k's, this becomes order k. And my total running time is k squared. So I'm going to do k operations, k extract mins. OK. Now the reason I wanted to entertain this is I claim it's going to be useful to help us find the answer. So everything that we have here gives us some insight into what the correct answer is. Well, what our correct answer is. There might be others. So let's think for a bit and see if we can do better. Am I covering something? I hope not. So by the way, when you have problems on your own, say you're looking at CLRS or at all the exams, you want to give yourselves half an hour or an hour to think. And just this process alone is going to help you do better on a test, because while you're thinking, you're going through everything you know, and you're rearranging stuff in your brain in a way that will be easier to access it later. So now you're going to think, what do I know about heaps? What do I know that takes log n time? What do I know that takes n log n time? And your brain will be better at answering these kinds of questions later. Now we're not going to give you 30 minutes because that would make us run out of time.
We want to reduce it down to k elements. Like,
I want to only have to look at k elements. That's good.
yes. I mean, otherwise you can't have log k because
Yep.
it's search.
OK, so that's good.
So, which is interesting, because if it's k log k, then that kind of suggests that you'd have k elements in the tree, but then you're searching for each one in the tree.
So maybe it's not, I'm not going to be able to
Yeah.
cut this heap into k elements, right?
Yeah.
I'll have to do a bit more.
Can we like cut this heap into k elements and use that heap to do our log k? Does this happen?
Let's see how we'd cut this heap. First off, let's see how this heap would look like if it's cut. How do we find the first k elements here? How do we find the first element?
It's just the first element.
It's the root. OK.
Extract min and then multiply.
Second element. OK. What do I look at? If I want to select the second element in a heap, how many elements do I have to look at? 2, 5, and 7. Because everything below will be bigger. Right? OK. I look at them, I compare them, I know 5 is the smallest one. Now suppose I want to find the third element. Who do I look at? 7 or the thing under 5. So 7 is still in the race for sure. And then I have to look at the children of 5. So, yep. Right now we're looking at 3. Suppose this has some really large kids, as in numbers, and I find that this is the third element. Who do I look at for the fourth element? Okay, so this isn't in the race anymore because it's the third. The fourth has to be either these two guys or the kids here, right? And it happens to be 7, so I take it out. If I want to look at if I want to find the next element, who's in the race? This guy gets out of the race.
7's kids and
Okay.
then, yeah, 9 the other kids.
Okay, so we have something, right? We're not really cutting up the heap, but we're sort of computing where the blade would go. if we wanted to cut it up in k elements and n minus k elements. Does this make some sense? Nods, no nods?
I mean, I guess you're never going to be going down farther than k.
Well, let's just understand the concept, and then we're going to do one more pass, write pseudocode, and understand the running time. Because this is still confusing, right? We'll need one more pass, otherwise we can't write the pseudocode and win. So does the concept make sense?
Is that k log k?
Yeah. So the idea here is that I have a horizon that says what are the next elements that I'm willing to consider. And first, the horizon starts with just the root, because I know that's the minimum element. And when I take an element out of the horizon, I put in its children. That's what I did all the time. So given a horizon, how do I know what's the next element to extract out of the horizon? The min. Okay. So I want a data structure for the horizon that can extract mins quickly. Okay, what am I going to use for the horizon? A min heap. Excellent. So let's try to go for pseudocode. Suppose we have H as our original heap. So H is a min heap. We will make Z be our horizon. I can't use H again. It would be nice if I could, but I'll use Z because Z is also a letter in horizon. So Z is a min heap. And then first I will insert into Z. I'll insert the heap's root, right? So Z dot insert H of 1. Remember that heaps are actually arrays. I hinted this earlier. So these nodes are elements in an array. So this is the first element, second, third, fourth, fifth, sixth. So we're using array-backed heaps, and H of 1 is going to be the root. Then I'm going to compute the first k elements like this. For k in range, for I in range k. So k is going to go from 1 to k. What do I want to do? Compute the ith element. How do I do that?
Extract min.
Ith equals z dot extract min. And then I want to insert the children in the horizon. Right? How do I do that?
It's 2i and 2i plus 1.
Okay, so this is if I know the index, right? But so when I'm putting things in the heap, the keys are going to be the values so that I can take out the minimum.
Was the empty heap first and then
Yeah.
inserted H1?
Yeah.
Right?
Yeah, okay. This is empty. This is empty, and this is the input. Okay, so I need to use the numbers as the keys. So when I extract something out of the heap, so when I extract the first element, it's going to say 2. It's not going to say 1. If I want to...
Why do z dot extract min then? Because
So this will give me the next key in the horizon.
But your horizon. Oh, I see. You're starting out with just the first one.
Yeah.
Oh, and then you want to add in the next.
So at the end of this whole thing, if I'm extracting them right, I can return this variable here. Because after k iterations, this is going to be the kth element. So I return it and I'm done. The problem is I want this guy's index too, right? So I can't just store the key in the heap. I have to augment the heap to let me store values, and I have to store the index. So for this guy, I would have z insert h of 1 and then its index 1. Then when I get out the ith element, I'll also get out its index. A variable name for that?
J.
J. Okay. Why would you name your variables like this? In the previous section, I had a similar suggestion, I. So why would you name your variables like this?
Doesn't matter.
Job security.
Come after it.
All right. So it's okay here. Try to not do that when doing an exam or an interview because it reflects poorly on you. For an interview and for an exam, you'll get us upset and we might be less lenient. Or at least explain what you're doing. So extract min is going to give us the key and is going to give us its index in the heap. What do we do afterwards?
We add to C.
All right, so when we take out 2, so we start out with an horizon of 2. When we take it out, 2 is the only thing that's in the horizon first. Then we take it out, and its 2 children get in the horizon. Then we take out one of the children and put its children in the horizon. So when we take out a node, we want to put its children in the horizon. So we're going to say z dot insert. What do I insert?
Each of I times 2.
J times 2.
See,
J.
it's working already.
Damn it.
The job security thing is working. And
2J's plus 1.
Or like Z dot insert.
Yeah, then insert teacher. You have to do 2 lines.
okay, sweet. So I go quick once. Okay. Does this work? I mean, does this do what we wanted it to do earlier?
Wait, we're extracting.
All right, first node.
I mean, if K is small enough,
Okay.
eventually you'll ask for something that is out of range of the array. Right?
Oh, so you're wondering, you're thinking that eventually these will run out
If you
of
have
range.
your really lopsided array, eventually you'll ask for something that's in the 11th row.
Okay. What would we want to do in that case?
It's one of those check to make sure that you're not going to point past the end of
Yeah, but otherwise move on, right? If an element doesn't have kids, we don't add them to the horizon. So we need some bounds checks, exception checking, things like that in here. And I won't add that because that will make it look long and ugly. So this is the idea. Okay, what's the running time for this? Good, cool. So creating heaps, initializing, all order 1, insertion. This heap is almost empty now, so this is order 1. Then these happen k times. And these are all operations on the heap z. And the heap for the heap z, it has some number of elements. And it's not always going to have one element, because every time I'm extracting one element, I'm adding 2. So, well, how many elements is it going to have at most? Okay, why is that?
Because of each time you add at most 1 element.
So I extract one for sure, and then I add at most 2 elements. So the heap size grows by at most 1 in every iteration. So the heap size z will have at most k elements. So now I know the running time for all these operations. What is it? Log k. Cool. So it's k times log k. And the reason that it works, it's a bit harder to see. You have to convince yourself, maybe using this bigger tree, that whenever you're expanding the horizon, you're expanding it the right way. So the idea is, again, that whatever path you take down, you're going to see ascending numbers. So when you're increasing the horizon, you're always pushing it down in such a way that your invariant is that all the numbers in the horizon are smaller than their children, and so on and so forth. So the horizon is always guaranteed to have the smallest number that you haven't extracted yet. And that's really the only thing you need. Okay, does this make some sense?
I don't think that would occur to me on exam, but
Yeah, exactly. This would not occur on an exam, right? Unless you think a lot, you're super inspired, all that. If it doesn't occur to you, what do you do?
go with the n-log k solution.
Okay, very good. Wait.
Or
Or
k log
k-
n.
Sorry.
Okay. K log n or n log k? Which one?
K log n.
Why? Two reasons.
K log n.
K log n is, so two reasons. Faster and simpler. So you write this down, and you get half score or 3/4 of the score, and you're done. It's better than not saying anything and getting a 0, right? I mean, 3/4 of a score for 2 lines of pseudocode is reasonable, right? 2 or 3 lines. This is 3 lines probably. Also, on most exams, we're humans, right? We might mess them up. We might make them too long. If we make them too long, you want to get the most number of points. You'll have time to figure out 1 or 2 problems at that level. But if we give you too many, for the rest of them, you want to have something simple that gives you some of the points. Same for an interview. For most interviews, most people don't really have a clue how many problems you can solve, how many problems are reasonable. So you want, for every problem, you want to show some solution reasonably fast and then see if they're happy. And if they're happy, move on to the next problem. And if they're not happy, only then spend more time. So this is as important as that. If you look at the recitation notes, we'll have some problems and we'll have some solutions. What are you going to do? Memorize the solutions? Yeah, you know how to solve more problems. There are probably 1 million problems in total. That doesn't get you very far. So what you want is understand this process that we went through. So every time we tried something, we got from some point to some point with a better running time, well, except for here, and where we had more insight on the problem. So this is the important part. And I'm going to show you one more problem really quickly. We're probably not going to be able to solve it because it's hard, but we're going to talk about it and see if we can get some insight. Let's see, what do I want to erase? This, I like that. All right, so we have an array of random numbers. 7, 2, 5. This time there's no order in it. 8, 9, I said 2 already. 4. And we tell you that the array has 2 to the n numbers to make the problem easier. 1, 2, 3, 4, 5, 6, 7, 6. So you have this array, and we want to answer queries of this shape. Say this array is E, and it has n elements, and you know that n is some 2 to the k. Minimum of all the elements from I to j. So you have 2 phases, just like we had on a problem in the exam. You have a pre-processing stage where you get the array, you do some computation, you save some information, and then you have a querying phase where you have to answer these as fast as possible. I see most people have unhappy faces. Bad memories, huh? OK, let's not worry about that problem. Let's look at this one. So assuming you have as much time as you want to do the pre-processing, what's the fastest way you could answer these? Yes?
You could do it, if you have as much time pre-processing, you do it O1, just memorize all the solutions.
All right, so pre-compute the answers to all possible solutions, right? How would I store that? So I want to do this in order 1. So how would I store these answers?
Just sort your array.
OK, so I store my array.
And then you want the minimum from I to j, just look up the ith element, and that's your minimum.
Oh, no, but your ij is ij in the original.
Oh, ij in the original. Yeah. All right.
Okay, so figure it out? Okay.
That's not valid.
Well, I mean, if I can sort it, I can also say, hey, why don't we use this array instead? And then I'll answer the queries.
Makes your problem really easy.
Yep. You can go off a tangent trying to sort the elements and keep their keys. The important thing is if you think about it for a while and you see that things stop making sense, back out, look somewhere else. We spent some time trying to find a solution based on sorting in my last section. It's not going to work. So
I'm confused, like why can't we just take the elements from I to J? Like why can't we slice the list and sort it and take them?
okay, let's get to that in a bit. So let's keep that in mind because that's another point on the trade-off curve. So if I want to answer my queries in order 1, then the way I do that is I will have a hash of all the arrays that look like ij. So all the possible intervals. And I'll store the answer here, right? The minimum of the elements from I to j. And I can do a hash lookup in order 1 and get the answer and return the answer. How many elements do I have here? So how much storage do I have to use for this?
So n squared.
Okay. N values for this, n values for this, so roughly n squared. What's the time for computing this? Brute force. Let's not think. What's the time for computing this?
Thank you.
N cubed. You're thinking. So I have n squared elements here. For every element, I have to compute the minimum of potentially order n elements, right? So this is n cubed. I could reduce it to n squared by noticing that if I have the minimum of these elements, and I want to compute the minimum of these elements, really all I have to do is compare this minimum with this element. So every time I start with an interval of size 1, and then I expand it by 1. So I have my 2 for loops here, and I keep growing my minimum. So I could get down to order of n squared time. So I have one solution that has order of n squared time and space, and then answers the queries in order 1. You had a solution, you said, where what you do is when you get a query, you compute this, right? You're suggesting sorting the array. That would be n log n. I would suggest not sorting it. You do the splicing, you look through all the elements, and you find the minimum.
No, like I was saying that take the original E, slice from I to J, and sort it, and then like.
Well, so when you get a query, the i's and j's are, yeah, they change for every query. Otherwise, we could pre-compute the answer. So we have one answer where we take order n time to answer a query. And what do we do for preprocessing? Nothing. Order 1. So these are two ends of a trade-off, right? One possible extreme is that you pre-compute all your answers. The other possible extreme is that you don't do anything and you brute force every answer. And now we want to find points somewhere on this line between the extremes. So the answer that we're going to show you in the solutions uses order n log n space. And it answers the query by using order 1 elements in this order n log n data structure. So I have order n log n partial minima, and I will only use 2 of them. So the total running time isn't actually order 1, but we only use order 1 elements. Let's start thinking very quickly. Let's think for about a minute, and then we'll go through the solution. And there are multiple solutions. All of them are interesting in different ways, and there are other solutions that are equally fun and applicable with not the same running time. Let me make some space here. So like I said, thinking is a useful process on its own. So you're getting better just by doing this.
Like, so we're only using order 1 space total?
We're using n log n space.
Oh, and it takes constant time to get the answer.
It will only look at 2 elements. It's actually not constant time. We're not going to worry too much about time.
Okay.
It ends up being log.
Okay, what was the order 1 then?
You only access order 1 elements, order 1 partial minima.
Oh,
Does it have to do with 2 to the k?
Maybe.
I don't know what to do with that, but
well, there's a
looks
log
useful.
there. There's probably some sort of tree involved.
So you're going to want to split things, right, into halves. And you're going to want to be able to do this all the time. And we say 2 to the k so you don't have to worry about, oh my god, what happens if the halves aren't equal. You can usually solve this when you implement the problem, but it's useful to not worry about that when you come up with your first algorithm, if you're going to start dividing in halves. So that leads to another useful solution. That leads to a solution that takes that has n log n storage, and it will run in n log n time with n log n element accesses. So what you're thinking of is you're going to have your array of elements, right? And say you want to find the minimum from here to here. You're going to have your array split in half. So you're going to find the minimum of this and the minimum of this. But to do that, you'll have to recurse. So this is also, say, split in half. So you'll have to find. So it turns out that if you do this, in the end, you'll have log n minima that you have to look at. But this is a cooler and more useful thing. So I'll try to put it on a pset or something to make you think about it. So this is, don't tell people yet. You might have a solution to a problem. Okay. So what we thought of, the way we thought of doing it is 6, 7, 2, 5, 3, 8, 9, 4. So we compute these partial minima. We split the array into 2, and these are the minima that we compute. Sorry, this is like this, this is like this, this is like this. So everything, so all the left half, then these guys, then these guys, then this guy. Everything here, then these guys, then these guys, then this guy. So if your I and j are on different sides of the middle, then you do 2 lookups, you're done. If they're in the same half, then you have a problem that's half the size. So you're going to have to take this array that's half the size, 2, 5, split it into halves, and do the same thing. And then we're going to have to do the same to this other one. 3, 8, 9, 4. Split it into halves and do the same thing. So in the end, you'll end up in some place where your interval edges are on different sides of the middle, and you look at 2 elements and you're done. Let's see how much space this takes. Can someone tell me a recursion for how much space, for how many minimums I would need to keep? So space for n elements is?
I mean, the first level you have 8 minimum, right?
Okay.
So, and then we go down by order of 2.
So what's the first level? So,
of 8n.
okay, so order n
Oh yeah.
plus,
N over 2. T of n over 2.
okay,
Right.
s because it's space, n over
Yeah,
2.
sorry, yeah.
Okay. And, yeah. You're missing something. Look at this picture. So this is the whole thing. Then I have a half. And then what else do I have?
2. That's
The other half.
Oh, 2.
Okay, so the difference between these two is that one of them gives you order n, the other one gives you n log n.
Yeah.
So I gave you the answer, so I can't ask you for the answer now. But where did we see this before? Pretend these are t's. Sorry?
Merge sort.
Okay, so if these were t's, this is the recursion for merge sort. So once you put it up, you don't draw the recursion tree and solve it. You say this is what we saw in merge sort. Therefore, the solution is n log n. So this is how you show you have n log n space, and it's pretty clear that you're only going to access 2 elements.
I didn't understand how is the not working here.
How it works?
Yeah.
So you have your I and you have your j, right?
Right.
Let's move right here. If you want to find the minimum, if I and j are on the different sides of the half, you have this and this. And these two partial minima cover your entire interval. Now if they're on the same side of the half, then you recurse to a smaller problem.
Well, you don't have 2 there, right? Because you already have the minimum of that section. If you have
Yeah,
5.
well,
It wouldn't work if you had 6 and 2, right? Or, yeah, for that.
yeah.
Well, why not just take 7 and 2 then? Like, why do you have to break up the entire half?
Well, assume there's more things there.
Oh, I see.
So if you have this, now it's no longer trivial, right?
Yeah.
So wherever they are here, you do that. And remember your pseudocode has to be as simple as possible to reduce the probability of bugs. So you want to do the simplest possible thing, not have special cases. Okay. By the way, there's a study that shows that for good or bad programmers, if you have 1,000 lines of code, there's a constant probability of a bug. And the constants are different for good versus bad programmers, but it's still a constant. So how many mistakes you make is directly proportional to how much you write. This is why we like simple solutions. Okay. Any questions on this? So we have 4 problems. We didn't cover one. Look at the other one. Look at the solution. Ideally, look at the problem, think for at least half an hour, then look at the solution. What I want you to take away is not just, oh, here are 3 problems. Let's memorize how we solve them, but the whole process thing and how we played with data structures and how we used all the hints that we possibly could to build more insight into the problem. Okay, cool.